The purpose of this video is to talk about accelerated motion. So we've talked about acceleration, but we really only focused on how fast are things going after a certain amount of time, right? Eventually what we want to talk about is, well, not just how fast, but how far. But before we get to that, I want to talk just a little bit about a problem. So everything that we've done so far with acceleration, we've been doing these charts to track what's happening over time. That's not really how problems get done. So let's look at a common, easy problem here. An object is traveling at 6 meters per second east when it begins to accelerate at, let's say, 0.5 meters per second each second west, right? Meters per second squared, or meters per second each second. And let's say it does that for 4.3 seconds. Now, the reason why I've chosen this sort of weird time is because when we were doing the tables, we were able to do that in even increment in intervals of time, and so it was really predictable and super easy. This wouldn't be easy to do, or it'd be kind of annoying to do by a table, which is why I want to show this methodology. So the question is, what is the velocity at the end of this time interval? All right, so if I'm doing this problem, what's my first step? Well, I have vector quantities, so the very first step is going to be to impose directionality on the page. So here we go. Let's say this direction is east, and we'll make that positive. This direction is west, and we'll make that negative. Cool. Second, a picture. Yeah, it's not really going to do all that much for us here. I mean, maybe I have, like, here's an object, a little car, and it's traveling east. And there is its velocity, and it's accelerating west. I'm going to just draw that here. So there it is. I'm not sure exactly what's going on there, but we'll kind of figure it out. So next, what I want to do is I want to decode the variables. So what I want to do is take every idea in this prompt and put it next to a variable. So first, I've got that. So that is traveling at 6 meters per second east when it begins to accelerate. That is my initial velocity. So VI is equal to 6 meters per second. Now, here's the thing. I could write east there, but if I want to do that decoding appropriately, let's use the fact that we've already made east positive. So there we go. So it's a positive 6 meters per second east. Now, a word on that, right? So 6 meters per second east is the velocity that this object has when I start caring about it. When I start the stopwatch, right? Who cares what happened to it before in its life, right? At some point, it had to achieve that 6 meters per second east, but we don't care about that. We're constraining the problem to be only the part we care about. Remember, we have the power of the stopwatch. Let's use it. So next idea I have here is that acceleration. So that's A is equal to, and here's the quantity, 0.5 meters per second each second, but it's west, so negative. And I know that's for 4.3 seconds. That is the time interval, 4.3 seconds. Okay, so I've decoded all of my knowns because I'm looking through there and there's nothing else that speaks to any other knowns. Now, what's my unknown here? What is that I'm looking for? What is the velocity at the end of this time interval? Well, that's the final velocity. So that's our question mark here. That's our goal. And this is going to help us in order to figure out what equation we need to use. Now, a word on this before we begin. I always like to stop and think a little bit about what my expectation for the answer is before I do the math, because that gives us a way of sense checking our answer when we're done. I have a velocity of positive 6 meters per second, or 6 meters per second east, an acceleration that is negative, or west. What happens when the acceleration is in the opposite direction as the velocity? Of course, that means that I'm going to slow down. So I'm expecting this answer to have a smaller magnitude of velocity. Great. So here we go. What equation links these two? Well, I have an equation for acceleration, which is acceleration is equal to VF minus VI over t. Now, here's the thing. What I want here is the final velocity. Right now, the equation's not set up for that. So oftentimes what I do is I like to solve the equation ahead of time for the thing that I care about. So here I multiply the t across and then solve for VF. And I'll just move VF over here. VF is equal to VI plus AT. Now, all three of these versions of the equation are the same equation. They're just different forms of the same equation. There's a word for that. These are isomorphs of the same equation. Iso meaning same, i.e. they're the same equation. Morph meaning change. So they're just changed versions of the same thing. In this class, you can start with any isomorph of the equation. So let's say I know this one, but looking at the information, since I know that what I want is VF, I would actually start the problem by writing that down as my premise equation, as my linking equation, because it's going to be the one that is most applicable for what I'm doing. So VF then is equal to, now I'm going to plug in with the units and solve, plus 6 meters per second. The plus there is redundant, sure, but I'm trying to emphasize the directions here because they are vector quantities. Plus a negative 0.5 meters per second each second times 4.3 seconds. You can take out your calculator and right, there's our little calculation sound, and you get, sorry, positive 3.85 meters per second, right? Notice here in terms of the units, and I don't have to do this unit analysis, but I do want to show you the seconds cancels with the seconds, and I'm left with meters per second here, meters per second and meters per second, overall meters per second. What I do want to do is then explicitly decode the meaning of that positive. So this object is still moving east at the end of that time interval. And as we predicted, it is going slower than it was at the start because the magnitude of the velocity is less. So there you go. Typical type problem if I'm trying to talk about acceleration and objects changing speed. All right. So now, like I said, the purpose of this video is to talk about displacement. Well, right now, we only have one equation that talks about displacement. But you'll notice here that the equation that talks about displacement doesn't have anything to do with acceleration in it. It is that the average velocity is equal to the total displacement over the total time. Now, as an isomorph, since I care about displacement here, I'm just going to solve for the displacement. Displacement is equal to average velocity times total time. So once again, we don't have anything here about acceleration, but that is the only equation that I know that has displacement in it. Now, the important thing here is that this term here is average velocity, but if we come back here, the velocities in this problem were all instantaneous velocities. So we're going to have to kind of like square that circle in order to figure out what's going on. So let's do a simple problem based on some work that we've done in order to see how we can figure that out. So let's say we have an object that is initially at rest. So VI is equal to 0 meters per second. And let's say we say to the right is positive. So left is then negative. So let's say I have an acceleration that is 4 meters per second, each second to the right. Or as I could write that, positive 4 meters per second, each second. So what I want to start out with is a table. Now I know I said before in the last one, when you're doing problems, we don't do tables, but here, usually what we're trying to show is a pattern. So here we go. We're going to look at time, and we're going to look at velocity, and there's going to be a third column on this table. So I want you to leave a little space there. So here's velocity, and here's time, 0, 1, 2, 3, 4, kind of similar to what we've done so far. So what do I have here? Well, I know at t equals 0, it's at rest, and t equals 1. Here we go. This is an acceleration of 4 meters per second each second. So this ends up with 8 positive 4, then positive 8, then positive 12, then positive 16. Right? That's our notion here. Now, I do want to say something here. this is a constant acceleration. What does it mean to have a constant acceleration? Well, if we look here, this chart displays it really well. A constant acceleration means that the change in the velocity each second is the same, right? So this is going to get really interesting now, because what I want to talk about here is eventually something to do with the displacement. I want to come back over here. Before, we haven't talked about constant accelerations. We spent quite a bit of time in class talking about constant velocity. So if I had a constant velocity of 4 meters per second, what that constant velocity of 4 meters per second is that the change in position each second is the same, which is very different than saying the change in velocity each second is the same. So hold on to that. Well, what am I going to do with this information? Well, every time that I've had a chart like this, eventually, hopefully you figured out what we're going to do is we're going to make a graph. The graph I'm going to make here is a velocity versus time graph. Okay, so velocity on the vertical and time on the horizontal. And so what I'm going to do here is try to put in roughly equal increments there. I probably made that way too long. 1, 2, 3, and 4. And then equal increments here. 1, 2, 3. So we'll make these 4, 8, 12, and 16. So if I plot this now, okay, 0, 0, 1, 4, 2, 8, 3, 12, 4, 16. I think it's pretty apparent that what we seem to have here is a nice linear relationship. So I'm just going to take a piece of paper here as my straight edge, and I'm going to drop in my best fit line, which is actually a perfect line. Awesome. So there we go. I have this best fit line, and what does it describe? It describes that as time goes on, this velocity is positive. This velocity is increasing, i.e. it's getting faster, right? That the numbers for the velocity are getting bigger. Now we'll do a later lesson where we'll focus reading velocity versus time graphs in a very significant way. We're going to focus on a couple of things here. First, I have a graph. It's a new graph and it's a linear graph. What's my question going to be? And if you figured out that my question is about the slope, then you are right, because that is what we've done every time we've ended up with a linear graph. So what is the slope of this line? Well, if you think about it, slope is delta y over delta x. But it's not y and x here. What is it? Well, on the y is velocity. So delta y is really delta v. And what's on the quote-unquote x is delta t. Well, what do you get when you have changes in velocity through time? Oh, well, actually, if I took the slope here, I would figure out that the answer I was getting is positive 4 meters per second each second, right? So if I did that slope calculation, I would find that what I'm getting here is what? It's the acceleration. And that is our fact here, that the slope of a velocity versus time graph is the acceleration. I'm going to box that because that's a hugely important fact. Now, let's use that idea that the slope of a velocity versus time graph is the acceleration to verify something. Notice this slope is positive. Notice the acceleration is positive. Notice the slope is constant. Our acceleration is constant. So there's a nice marriage between those ideas. All right. So I said at the beginning that the point of this video is talk not about how fast things are going, because we kind of covered that, but about how far things are going, meaning what is the total displacement? Well, I know after 0 seconds that the total displacement has to be 0. Remember, displacement says how far from where you started. After 0 seconds, you are never any further from where you started. So clearly that has got to be 0. Now, here's the thing. After 1 second, how far do you think that this object has traveled? I want you to shut off the video for a second and answer that question. All right, hopefully you have an answer to that. Now, if you just went with your gut, most likely what most people say is that after 1 second, because the object's speed or velocity is 4 meters per second, that this thing has traveled 4 meters. Okay, how many people have said that? Well, obviously I asked that question to the void. Hopefully you're raising your hand to yourself if you said it, and if not, well, we'll see. Notice I wrote that in red. Why did I write that in red? Well, that's obvious then, because it's wrong. What? Why is that wrong? People say, hold on a second, the velocity here is 4 meters per second. How come if I traveled 1 second, did I not travel 4 meters? And that's what the graph is for. Take a look down here. When is this object traveling 4 meters per second? Hopefully you're noticing, because this velocity is constantly changing, it's only at 4 meters per second exactly as it gets to 1 second. A little before 1 second and the velocity is less than 4. A little after and it's more than 4. So therefore, the object couldn't have traveled 4 meters in 1 second because it wasn't traveling for 4 meters per second for the entire second. In fact, for most of that second, it's traveling less, well, not for most, for all of that second, it's traveling at less than 4 meters per second and only gets to 40 meters per second, 4 meters per second at the very end of that second, instantaneously at the end. So what does that mean? Well, what would need to be true for the object to have traveled 4 meters in that first second? One of two things would have to have been true. One, it was traveling at 4 meters per second the entire second. Or, going here, it would have to have an average of 4 meters per second for the entire second. Neither of those things are true. So, what does that mean? Well, looking at this, what do you think is true about how far the object travels in that first second? And hopefully what you said to yourself is some number less than 4 meters. Why less than 4 meters? Well, because for most of the second, you're traveling less than 4 meters per second. But how do I figure this out? Well, here goes. It's this equation is the guiding light. It says that the displacement in an interval is the average velocity in that interval times the time of that interval. So let's just highlight that. This is the average velocity in the interval, okay? Notice these are all instantaneous velocities. So in order to do this problem, I need to know what the average velocity in the interval I care about is. So let's pick an interval. The interval I'm going to pick is t between 0 seconds and 1 seconds. So just quickly, interval notation. If we're going to be really proper about this, which I'm generally not going to be, but t is an element of, right, between 0 and 1, and it's hard brackets because I'm trying to include 0 and I'm trying to include 1. Well, if we looked at this thing starts this interval with a velocity of 0 meters per second, and it ends the interval going 4 meters per second. And there's the trend. If I forced you to say, well, what do you think is the average velocity in this time interval? What would you say? Okay, hopefully your gut instinct said, well, the average velocity in this time interval is 2 meters per second. Well, why is that? Like, what is behind that intuition? Because I'm going to tell you, it's the right answer. But we have to have a reason, and we can't just trust intuition. Well, why is that true? 2 meters per second. I think that the easiest thing to say is that 2 meters per second here is the median value in that interval, right? So, oh yeah, it's just the median value in this interval. So here, the median value of the function in the interval, and we're going to say is equal to the average or mean value in that interval. And I'm going to have a because here because that's not always a true statement, right? Well, why is that true here? Well, if you think about what averages are, averages adding up all the quantities and dividing by the number of quantities. So if you think about it, 2 meters per second. If I go a little bit bigger than the 2 meters per second, there's going to be an associated value that is smaller than 2 meters per second on the other side of that value. So for every value bigger, there's a value smaller, and they kind of like match out and cancel out. Now, why is that true? That's only true because this function is linear. So the median value of the function in the interval is equal to the average value of the function in the interval because the function is linear. If the function weren't linear, that wouldn't work. Why is this function linear? Well, this function is linear because the slope is constant. Oh, and the slope is equal to the acceleration. So this is true because the motion has a constant acceleration. Okay, and so that's going to become important for us, that when the acceleration is constant, the median value of the velocity in the interval is equal to the average value of the velocity in the interval. Okay, and the great thing about this course, folks, is that we're only going to be dealing with constant acceleration problems. It gets really, really, really complicated for reasons we'll talk about if the acceleration is not constant. So how then do I calculate this, right? So very simply, to find the median value of a function, you take the first value in the interval and the last value in the interval, and you divide by 2, right? That's how you find a median value. And we're going to say that that's equal to the average value. So we're going to box this, and that's going to become an equation for us. But this equation is not always true, folks. It's only true if the acceleration is constant. So if and only if, right? If, one of my faves. There you go. So that's how we're going to do this problem then, is we're going to use the notion of average value. Because if we look here, I can then do the problem properly. I can say that the average value in that region is the initial value plus the final value divided by 2. And then I can plug in for this interval 0 meters per second plus 4 meters per second over 2 to get 2 meters per second. And then I can come over here and say, well, then the displacement is the average value of the velocity in that interval times the time of the interval. So it's an average of 2 meters per second for an interval of 1 second long. And that gives me that I travel 2 meters in that time period. And so there you go. We can come back here and we confirm our guess that it's less than 4 meters per second, and it's in fact 2 meters per second. All right, let's do one more interval together, and then I'm going to have you do something by yourself. Let's say the interval that I care about is between 0 and 2 seconds. Well, why is that the appropriate interval to look at? Well, if you notice, what I'm trying to do is fill in here. What goes here is not how far it goes between t equals 1 and 2, but how far in total it's gone from the start. So the interval in question here is from 0 to 1, from 0 to 2, from 0 to 3, from 0 to 4, okay? So here's my interval from 0 to 2. And so what's the initial velocity in that interval? It's 0 meters per second. The final velocity in that interval is 8 meters per second. So I can calculate the average velocity in that interval is VI plus VF over 2. Always write my equation, plug in with units, and an answer with units, 4 meters per second. And therefore, how far in total do I go? Average velocity times time, and that's 4 meters per second. But now the length of the interval is 2 seconds. And so 4 meters per second times 2 seconds is 8 meters. And so there we go, 8 meters. What I'd like you to do now is to shut off the video and find how far in total it's traveled to 3 seconds, how far total it's traveled for 4 seconds. Great. Hopefully you shut off your video and you did that work, and what you got was something that looks like this. And I just kind of put it all together in a nice little way. We can see our average velocity of 2 meters per second for 1 second is 2 meters. Average velocity of 4 meters per second for 2 seconds is 8 meters. Average velocity of 6 meters per second for 3 seconds is 18 meters. Average velocity of 8 meters per second for 4 seconds is 32 meters, right? Notice that depending on the time interval, the average velocity of that in that interval is different because the median value of the function is different in that, okay? And then if we put this all on our table then, there we go. So what we can see here is a really important thing. Remember when we were talking about constant speed, we said, what's the velocity, what's the hallmark of constant velocity? And we said that it changes position by the same amount in equal time intervals. Here, this object is speeding up. So in equal time intervals, if you notice here, it moved 2 meters. But here, it moved 6, here, 10, here, 14. In even time intervals, the interval displacement increased. That's what we said speeding up means. And so our pattern of data matches exactly what we said we should expect. So there we go, right? So we now have a way of finding out how far. What is that way of finding out how far? Well, very simply here, we know we have a couple of equations. The first is average velocity is total displacement over total time. We now know that average velocity, if acceleration is constant, is equal to VI plus VF over 2. And we know that the acceleration is equal to VF minus VI over T. Okay? Now, these are 3 of the what are called kinematic equations for vector quantities. Okay? There are 2 more of them, but the homework problems that I'm going to assign you, you can solve using these 3 equations. What we'll find out is the 2 additional equations actually make some of these problems quite a lot simpler and make them one-step problems. But I don't want you to go looking them up. I want you to solve the problems I'm going to give you tonight using just these 3 equations so that when we meet on Friday to talk about the other 2 equations and get you doing more problem solving, you appreciate them more. Because if you do it the hard way and then I give you an easier way, you'll appreciate the easier way more. So that's what we're going to do with these. So we're going to practice with these notions. Other things that we'll talk about is we've made this other pattern of data with our displacements. So we're going to talk about the displacement versus time graph that goes with this, but we're going to do all of that later. For now, we have enough information for you to be able to solve some problems to answer the question, how far has something gone while it's accelerating, by using this grouping of equations and the understanding from this video.